musical effects. And
Oh, yeah.
you
Just usually use a tin cup.
A tube, yeah.
Yeah, nice. Nice. All right, hello and welcome, viewers. There's probably an ad right now, but that's all right. I'm going to talk anyways. Today we're continuing on with the history of mathematics. And we have Adrian taking us on this journey, and what a journey it is, and what a journey it has been so far. So, Adrian, if you could please
take it away. They story, them stories, her stories. No, his story. And junk.
Z story.
The story. La storia.
So I'll try to regroup. Basically, I have to. Oh, what's that fancy? I'm easily distracted by whatever's that falling out of the. It's like bird feathers from when the murder cat killed it. It's like I'm not totally crazy, but there's like, why is there feathers falling from the sky? The sky is falling. I'm easily distracted, and I purge a lot of math in a frantic way a lot of the time. So we're gonna try and wrap it or rein it back in and give PDFs based on the history of math that we did so far. So I was taking us through the journey of where's this PDF that I have too that I have to rely on. There it is. So we're taking a journey on what the real numbers are essentially in an intuitive manner, and how we develop the different kinds of numbers from the mists of time way back when our species was forming language, etc., to Mabel. Oh. It's like I just blame it on the offspring. Mabel, why is there noises happening?
Sorry, man. Sorry, Mabel. Okay, you're good.
We're blaming Mabel anyways. Now what was I saying? I heard a noise and then it's...
Mists of time.
So we want to go from the mists of time up to, I was doing approximating the square root of 5, etc. And then we got into the interesting discussion of if the square root of 5 is approximately equal to 2.236, etc. Last time I coincidentally, I didn't even know it was a 6, but I had said that they say we get a 2.35 and a 2.237, and those are you're always going to get an overestimate and an underestimate. So the square root of 5 will go right in here, and that's one of the last things we were talking about the decimal expansion of numbers. And then if you subtract these two numbers from each other where you get zeros. If I did that right, I'm bad at subtraction, so be careful. I have to double check. But when you do that, now you know that this digit was correct, the ones digits was correct, and then the first decimal digit and the second decimal digit was correct, but then this one wasn't. And then someone was asking about, well, shouldn't you write it as 2.24 because the next digit is a 6, and if you're going to truncate it and round it, shouldn't we round because it's a 6, the next number is a 6? And the answer is no. When we're playing this game, we're playing the game of how did your calculator know that it was 2.236 so that you could round it. What I want to have in the computer's floating point, whatever it is, 8 or 16 point floating digits. I want to know exactly what the digits are, and then if you're doing some homework problem, then you can do your rounding business. But I want to know what the actual digits are. I want to know that it's a 2 and a 3 and a 6 with no rounding specifically. I'm trying to find the actual digits. And then also, when you do that, if you had that number, we can do one where I know 8 of them, 3.1415926. Wait, 2, 4, 6, 8. There, so there's the 8. So say you have that in your computer now. If you look at that, oh, it was a 3.5. But it was a 3 next. So have they rounded it down, or have they truncated it up, or are they ever truncating it? Or if it gives you this one, if I truncate to 3.1415, even though the 9 was next, do you notice how I didn't round it to 3.16 because I want to know what the actual digits are? And how does your calculator know what the actual digits are? And it's not even in that floating point, whatever it is, it's not rounding them the way that we would train you to round. So that was the first approximation I did. And then today what we can do to segue into that is I started talking about decimal, so let's talk about the arithmetic and other bases. And also in the PDF files that we're starting to put up, there'll be two versions, I guess. One of them will be ones that'll be basically just a couple pages and a light read about the topic with minimal math. I'll try to keep the number of equations down to a minimum in those ones. And then if you want to see the gory detail and support us on Patreon, etc., we'll have all the gory details of all the theory and all the proofs of all these statements and a bunch of calculations for them, anything that we don't do online. So what do we mean by arithmetic and other bases? I gave a theorem last time that says for any b larger than or equal to 2, there is a unique base b representation where we take a bunch of digits d0, d1 up to dk, say to if there's k digits in your number, and then there's the in element, and then what we're going to say is we're going to have a set, and we're going to have 0, 1, 2, 3 up to b minus 1. If you pick a base b, we'll do this in a second. Actually, let's do this right now. So whenever in theory they're doing this to you, what you want to try and do is give yourself an example. So the two that I use is 7 and 11, and you'll see for reasons there's twofold at least. They're both primes. One's less than 10 and one's larger than 10. But if I do that for 7, I would get 1, 2, 3, 4, 5, 6 is 7 minus 1. So in the theory, it looks slightly different, but that's all they're saying. And notice that these are the remainders when divided by 7. So any number that is divided by 7 has to leave a remainder between 0 and 6. And so we collect those digits. We'll use long division in our in our process today. And the key to the numeration system was all I need now is in base 7, all I need is those 7 digits, and then 1, 0, 7 is one group of 7 plus 0 groups of 7 to the 0, and then that is 1, 0 in base 7 is 7 in base 10. And so that's going to work out in any base. 1, 0 in base b is equal to, by definition, 1 times b to the 1 times 0 times b to the 0, which is b in base 10. And then there's the binary joke. That one. There's this many kinds of people in the world, those who know binary and those who don't. So let's get into representing in there. And then what we're doing with the positional system, the definition of positional system in any arithmetic, including the decimal notation, is what we do is we write a number n, and then we write it like this. We write it as, it's backwards because of the Arabs, Muhammad ibn Musa al-Khwarizmi. He writes it right to left, so it's going to be dk minus 1 up to d2, d1, d0. We write a string of digits for a number. Well, I'm going to emphasize when it's not base 10 in familiar land that we're going to now try and do this in base 7, and we're going to consistently try to talk about apples in a basket, because you'll go hungry if you think that there's 1, 2, 3 apples in the basket. If you think you have 123 apples in the basket, but then it's base 7, not base 10, there's far less apples than you thought in the basket. And then we'll get into that. So what is this by definition? This is the numeration system. In any numeration system, what you do is, the epiphany that Brahmagupta and Aryabhata and a few of these people in India have first is all you need is a 0 for a placeholder of nothing, and then the digits of the positive remainders when you divide by the base, and then you can create as powers of b. You also need to know the definition of b to the 0 is 1, b to the 1 is b, b squared is b times b, b cubed is b times b, etc. And then when you have positive powers of this, what we're going to do is combine this notion of exponentiation and this guy to the definition of this is exactly dk is multiplied by the appropriate power of our base, b to the k, plus this digit will be multiplied by b to the k minus 1, plus all the way down to d1 will be multiplied by, well, I guess we can put this in. We have this in our language for the 10. If I go dot, 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 and I do d3 b cubed plus d2 times 10. See, my brain already wants to put the 10 in there. The b squared plus d1 times 10 plus d0. This is the one spot, because they call it the one spot because b to the 0 is 1, and then this one I have put a 10 in there already again. That's going to be the 10s in our language. 10 is the word that we're going to use for that. 100 is 10 squared, and then 1,000 is 10 cubed. So we have word for that when the B is a 10. When B is 10, we get 1,000, the word, 100, and 10, and then 1. And then it's the ones because 10 to the 1, and all these guys are ones. So this is the numeration system of now, unlike the Roman numerals, we no longer need to keep inventing new symbols for the numbers. We can have a finite set of reasonable amount of, and that's why 10 will be the Goldilocks land as well. It's just right. Binary strings of digits get really long, really fast, even for a short, fairly reasonably small magnitude number. But there's only two symbols you need, zeros and ones. Base 60 means that your strings of digits will stay short for a long time, but you have to memorize a 3600 multiplication and addition table, which is going to be exhausting for most mere mortals. So we pick 10 like the Egyptians noticed, and we use a sub-base 10, and we're going to float in that. But now what we're going to do is we're going to take a journey into base 7 land and base 11 land from the decimal land, from the familiar one that you already have. And then we're going to do adding and multiplying. Why you borrow the 1 digit, and etc. Once you do it for the 7 and the 10, this is going to be what I'm trying to do for you right now. Is the same thing as no one knows their own language until they've learned someone else's language. So you learn a lot about your own language and the rules about it when you try to learn and map it into another language, like that dirty Italian language or whatever it is. Once you learn Italian and you learn some phrases in Italian and German, sprechen Sie Deutsch, you learn about, it's like, I didn't even know, before like age grade 11, how old are you, Mabel? 17 almost? Before 17, I didn't even know what a nominative form or I still don't know what a nominative form or a dative form is. Accusative. That's like, who am I joking? I didn't know, but I still don't know what those are, but I know that they exist now. So what I'm trying to do in that analogy is I expect that you know what base 10 is, or decimal notation, and you've muddled around with it with your calculator for your whole life. What I'm going to force you to do is learn another language. We're going to do this whole game in base 10 that you're familiar with base 7 and 11, and we'll look at the slightly different nuances of that, and then it will make when you go back to your familiar base 10 and live the rest of your life that way, it will make it a whole lot more pleasurable, hopefully. Or I'm going to ruin it for you on any given Sunday. So let's do it. What do I want to do, So what we're going to do is let's look at the difference between writing them in. Let's look at the difference between. I'm going to keep redoing lines for the live people, the 3 live people, for Lorenzo editing. And Lorenzo, you're editing all these, by the way.
Wait, what?
wait a second.
We're live.
For whoever does this later, yeah, we might try to make these into videos and editing, so I might do my lines a couple more times. I've been trained well. He's cracking the whip. He's yelling Didi Mao behind the scenes, and I told him that's racist and he shouldn't do that.
Done, yeah?
But it doesn't stop him. All right, let's look at the binary. And then what would it be? Heptary, 7. And then unary for base 11. So this is going to be B equals 2, B equals 7, and B equals 11. I just pulled those out of a hat that were in. There's a hat inside my head. It's not on my head. But, but I just pulled them from there. And then what does that mean? So let's build this in each one. But Leibniz realized, what I realized was my coffee was gone. What Leibniz and the Chinese and everybody realized was all you need is zeros and ones. So our decimal digits, our binary digits, called bits, binary digits, all you need is zeros and ones. And then you can describe everything in the universe. For 7, notice that what we're going to do is we're going to use 0, 1, 2, 3, 4, 5, 6. Now there is no symbol. We're going to throw away 7 doesn't exist, 8 doesn't exist, and 9 doesn't exist anymore. That's why, because 6 was afraid of 7, because 7, 8, 9. Wow. Those ones work better for the grade school kids when I do them. But we're going to get rid of all 3. We got rid of all 3 of them. So what is now, but now that I've crossed those out, those numbers still exist, just those symbols don't exist. So what is 7 in base 8 in base 7? It's going to be 1 0. What is 8? 8 is 1 1 now. And what is 9? 1 2, because that's going to be our definition. 9 in base 10 is 1 2 in base 7. Why? Because that's one group of 7 plus 2, which is 9. So we have to think how many apples are in the basket. That's going to be our new symbolization. The magic, so we threw away symbols here. The more exciting thing with 11 is we get 3, 4, 5, 6, 7, 8, 9. But now I can't use, 11 is going to be 1 0 in its own base. So I need a symbol. I'm going to use lowercase alpha. There's a convention online, etc. for this. The American, I don't know why it has to be the American always, but the American Society of different numeration systems and the symbolization. I think they use lowercase Greek alphabet or these types of things. The other one that you would have seen is from Matt Damon. Hexadecimal uses base 16, and this is good from The Martian. When they do in The Martian, he needs 16 degrees of freedom. So what they use is 0 to 9, and then they use A, B, C, D, E, F for 10, 11, 12, 13, 14, 15. So those would be the symbols that we would use. But the point being is, you get to the exciting part is you get to the epiphany of what had to happen couple thousand years ago when they're doing this. You get to invent your own symbols for the notion of what 6 is or what 7 is or what 10 is. 10 is now this symbol, unique symbol alpha. And then in hexadecimal, they just used capital block letters for 10, 11, 12, 13, 14, 15, and then we write our symbols. So if I was writing, say, 9E2 in base 16, what that means now by definition is, and if you do this because it's backwards, if you're Canadian or European, because it was Arabic first, they were going this way. So what I like to do to write this out for yourself so you don't hurt your brain is this should be 16 to the 0, 16 to the 1, 16 squared. I write it above. I want to make my own wizard notation for this, but powers that be. So now what does that become? That becomes 9 times 16 squared plus E times 16 plus 2 times 16 to the power 0. What was E? E is 14. So now this is going to be 9 times 16 times 16 plus 14 times 16 plus 2, and I do not care what number that is. So some number, you can do that. Put it in the chat. What is it? First of all, the 16 squared would be 16 is 2 to the 4, so that's 2 to the 4 to the 2, which is 2 to the 8, which is what? 256. 256 times 9. Some kind of number. We're going to, the irony is what we're going to do is 256 times 9. I'm not going to use a calculator. And then 14 times 16. You have to do this as well if you want. All right, let's do it. So 9, and then this is what in your head, this is exactly what I'm going to talk about. In base 10, what do we get? I don't know what that is. 54? I don't know. 9 times 5 is 45, and then we're going to get 9. We have to add it up, 49, and then 9 times 2 is 18, 19, 20, 21, 22, 22. So then we get 2294, and then we have to do 14 times 16, and then why do you write the 0 down there? So this one, first of all, you're going to get 24, and then we're going to get 8, and then you write a 0. Why did we write a 0? Because now we're in the 10 spot. It's not going to add anymore to the 1 spot. So then we get 4, 1, and then I get 4, 12, 2 plus 224 plus 2. I can do that one. That's 226. So then let's add that one. 226 plus. This is how you do actual math because it looks not so surgical. That was 9, 10, 11, 12, 5, 2. I got 2520. Is that even remotely close? I'm not very good at doing that. Just a second.
I think so. You have to use a better calculator.
Based on the calculator, that's what worked. Notice I did it all by hand because that's what we're going to do in a different base now. We're going to figure out how that worked in decimal in the other bases. All right. So let's go back to for pedagogical reasons, for the rest of the video, let's do base 7, and then we can do a gory detail of a whole file with 7 and 11. I have a bunch of these other bases in there. So let's say we picked base 7 now. And so we know our decimal digits are 0, 1, 2, 3, 4, 5, and 6. What I want to do is, let's do the first thing we're going to do is conversions. We want to go from familiar, which is decimal. Why do you have a squeaky, 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 squeak? That's what it's officially called, squeaky, 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 squeak. If it's like, you have to add 3 onto it, because if it's I just like that, then that just means you like it. But if you like it, that means, oh, then it's getting serious. And then if you like it, then you give it thrice likes, then you know you're really serious. So this is familiar land, and then we want to go back and forth to unfamiliar. It might be all unfamiliar, like me spelling English. That says familiar. Unfamiliar. And that's going to be base 7. I don't know how to spell. Let's do the easy one. Let's do from base 7, or base B in this case, which is 7, to base 10, which is decimal. All right, so well, let's not even do it in theory, let's do it by rote. Let's do 1, 2, 3 in base 7. How many apples do I actually have? So when we think about this, we're talking about apples where I'm thinking my brain in decimal notation, and I would actually know how many apples I have. So if you think you have 123 apples and you're about to give them out to people, this isn't going to work. You could divide it by 3, because 1 plus 2 plus 3 is 6. So there's a 3 times what, 37 is 123. So we could divide that up between 3 people, etc. But it's not going to be 123 apples. We want to ask ourselves how many apples are actually in the basket. To convert from base 7, the weird land, to your familiar land, base 10, all you do is use the definition. By definition, this is a string of digits. All the digits come from my familiar in here. All I did was pick 1, 2, and 3. And then this is 7 to the 0, 7 to the 1, 7 to the 2. So this is 1 times 7 squared, plus 2 times 7, plus 3 by definition. Now you just convert everything in your head that you've always had all along in your multiplication base 10. 7 times 7 is 49. 2 times 7 is 14. And then plus 3. So now in my head also, I don't know why they always told you to do it like that, because when we actually add things, I want to do it vertically. So we're going to do 49 plus 17. And we're going to get 16. And then, 66. So this is, you only had 66 apples in base 10. So that's how many apples you actually really had. How do we convert the other direction? So if we want to, we actually have to use long division. So let's do theorem, the division algorithm. If you want to use Dr. Google to look it up, it's nice to have a name. What this says is, for any 2 integers, positive or negative, we can make them positive if you want. Yeah, I'm going to sneeze. Don't do it. There must be something on the board, whatever I used to clean it with.
And you're muted. Sneeze away. Give her. No one can hear you. No one can see you. You are free. All right. So yeah, there we go. That's different bases now for numbers. This was one of the most eye-opening things to learn about numbers and math, is just different representations of them. So you have this abstract concept known as number, but then they can be represented in many different forms. Oh, Adrian's back now. Here you go.
Woo.
You're up.
So yeah, what you were talking about, I'm going to guess too, is we could use a pebble to represent 1, or we could use a stick to represent 1, or we could use I to represent 1, or we could use lowercase I, or we could use the symbol this, or they started making it fancy. And all of these things represent the same thing, the symbolization for the Platonic notion of where one thing is, one pen, one person. But now we can represent them. It didn't magically have to be base 10. It's probably base 10 because of the hands that we use. This one, I'm going to be phrasing, all the algorithms are going to be phrased in base 10, but you can turn them into different bases if you want. But if we have for any two integers, let's make them positive. I can show the algorithm later if you really want to get into it, but we're going to use positive integers at first. So strictly less than, I'm going to make b the smaller one. So divisor, dividend. For any two numbers, we have, so this is existence and uniqueness. Oh, and a kitty. Hi. I know. Well, you came down here and you're going to make me sneeze too, probably, because you were just, it looks like you were rolling in the dirt. Hi. This one's Willa. Hey. You know about math and stuff? Oh, so kitty. What do we have, Willa? We have unique. I know, that's exciting. Yep, she's reading it. It's like you spelt that weird, right? We have unique integers. R, let's do Q first. Q and 0 is less than or equal to R is less than or equal to B minus 1. Notice that those are the remainders. Those are going to be our decimal digits, such that, and this is the uniqueness part, if you make the remainder negative, you can have infinitely many remainders, but there's a unique one which is positive and less than B, right? Yeah. Such that A is some multiple of B plus a remainder. This is the division algorithm. We can use this. We used a version of this to do Euclid's algorithm, which we're going to talk about in its gory detail all over the place in this with Diophantine equations and the Enigma machine and everything else. You're being very well behaved. I thought you were going to struggle more. No, you love me? I know. You can't fake cat love. Kitty. And then right now what we're going to do is, I know, easily distracted. We're going to use the warmth of the kitty and her love and some coffee and this algorithm to generate a conversion from base 10 to our unfamiliar land, right? I know, let's do it. Let's do it. Okay. I smell like coffee. Okay. You're heavy, cat. You're heavy. Go bother Tom, or go bother Tim. Go bother Timmy. Go get her. Yeah. I had to just nudge her. Now she's on her way. There's that kitty. Okay, so we're going to use that division algorithm. Basically what that says is, in plain English, you can divide a number into another number and you can get a unique quotient or remainder. Also, if you want, because we should pedagogically do this a little bit, this was B, Q, and R. B is called the divisor. This is the dividend. You want your money back in dividends, multiples of the original amount. Dividend. And then this is the quotient. And this is the remainder. This is what I get to eat when we divide the jelly beans into my daughter's friends, and then there's 3 left over. I get to eat the remainder so that everyone's fair is fair. I'm praying for a non-zero remainder every time I divide the jelly beans. Otherwise, I don't get to eat anything. Till next week when they might pay me. All right, let's do the conversion. Conversion. That's supposed to say conversion. I don't know what that said. There's something slimy on version from B equals 7 to B equals 10. No, I just did that one. Let's flip that around. So now that we have familiar land, if I have 1, 2, 3, how do I actually convert that to base 7? This is in base. So when I don't write subscript 10, that means that the number is, like you've always used, that is 123 apples in it. That's one group of 100, 2 groups of 10, and 3 ones, which is 123. That's why I like German. That's 103 and 20 still, which is slightly better. We'll get into that when we talk about the Huns, those damn Huns. The barbarian horde. We got to keep off the barbarian horde. So what are we going to do? We're going to use this as A and then we're going to use B coincidentally as 7. And then I have to divide that. I'm going to use the division algorithm. So first of all, here's the symbol that I use if I'm dividing 7 into 123. Here's what they didn't tell you, and you can see it for the first time. I don't think I've talked about this on the Wizard channel yet, but the reason why you didn't like long division when you were younger is when you had a really big number and say it was a 17 or a 19 or a 23 or something like this, what you're asking yourselves is, what's the closest I'll say it even in rhetoric, what's the closest multiple, and this one's easy to answer, but it can get really hard really fast. That's what she said. What's the closest multiple of 7 that goes into 1 or 12 or however you want to start this? I'll start it properly and show you, but they say 12 that doesn't go over. And then you start saying that, and I start so don't do that. Write the multiples. 7 times 1, add it to itself, 14. And then add it to itself, I get 21. And then add it to itself if you have big numbers. I'm showing you how to do it. I know what they are. 7, 14, 21, 28, 35. You want to add these 42, etc., and then times 2, times 3, times 4, times 5, times 6. You only have to go to 9 because in decimal notation there's only 9 remainders, positive remainders. Now what I'm asking is, how many times is 7? How many times does 7 go into 1? None. And I have the outcome. So then I write it down, I subtract, I get 1. I bring the next one down, 12. How many times does 7 go into 12 without going over? It has to be right in here. So it has to be 1 time, and then I get 7. I subtract, I get 5. I bring it down, I get 53. And now you can also see now here it's important. How many times does 7 go into 53 without going over? Oh, it's down here, 49 times 7, and then 56 was the next one. I didn't write them out already, but 53 goes in between those ones. So it has to be 7. And then I know what the outcome already is, 49. And that speeds up drastically how fast you do your long division, and for lack of a better phrase, how fun it's going to be. Because now that I have all the list of the outcomes of the multiples of the guy that I'm dividing by, and I have what those quotient pairs are going to be, I can do this game a lot faster. This I have a hard time adding still. What is that going to be? 4. It's like now I get nervous. That's all the theory. I'm like, good. And it's like, shit, now I have to freaking subtract those numbers. Danger. 4. So what does that say? If I did this correctly, in our first step, 123 is equal to 17 groups of 7 plus a remainder of 4. And I started using brackets on purpose to emphasize what we're going to do. Which 2 numbers do I pick next? You always use the base 7 and you use the number in the brackets. So the next one I want to do is 17 into 7. And we're doing it every time. It shouldn't be too hard this time, because what are we going to get? How many times does 7 go into 17 without going over? It's going to be a 2. I get a 14. I get a 3. So that says in each step, even if you can do it in your head, that's technically what you're doing. And this is technically what I'm using. And then after you're done, this is how you will probably feel. You just drool a little bit and lay on the ground. It's all right. It's all right. It happens to the best of us. But now 17 is going to be what? 2 groups of 7 plus 3. And now here's where you know you're done. When this number becomes less than the 7, that says we have to do the dirty trick of 2 is no groups of 7 plus 2. I like this one. I always pick this one because 1, 2, 3 becomes 2, 3, 4 in base 7. Never mind. That was my happy dance. You're not going to get it to see it again. Rewind it and make a meme out of it if you want, but that's as close as...
Already recorded.
It's
Yeah,
already
we're good.
recorded it. We're already making it into a meme. This is what a wizard dance... Oh, this is cutting a rug. So now what is it and why is it this way? I claim... And don't just take things verbatim and truth in the world, especially these days. The news said that was true, so fake news, that's fake news. Some guy that's going around espousing that a lot of this news might be possibly fake. I claim that 1, 2, 3 now in base 10 is 2, 3, 4 in base 7. Do you believe me? There should be a justification for this. So how do we get this justification? We're going to back substitute. Is what we're going to do. So in terms, this is what you would do to prove it also. So what I'm doing also by rote is what the theorem will say is in the division algorithm or this conversion business is if I have a number in base 10 or in any other base, you could do this as well. And I use this long division process. What's going to happen is I claim that it's going to be the remainders in the reverse order will be the new decimal expansion. So I took the 2 and the 3 and the 4. But why is that? Well, because what we're going to do is we're going to use some algebra and the definition of numeration system. So it's like a one corner problem. Basically, all I'm using the definition and a little bit of algebra, and then it should just fall out why this is true. So I'm going to do it by rote. The first thing that the theorem claimed was, I didn't really write the theorem out. I wrote out the lemma to the theorem. What the theorem is saying is if you have a number in base 10 and you use this iterated algorithm where you use the quotient every time until you get a 0 quotient, the remainders in that process will be the new base B expansion for base 7. I like Mean Machine Rex. He used quantum mechanics jokes. Algebra. But we want it to be a bruh. Do they have? Is that the bruh? Yeah, you're right, because this has to be the ket.
Well done.
Well done. You get plus 2 points. You're like, I didn't know there was an exam. There's always an exam. It's always a test. There's always a test. Now I forgot what I was doing because I'm impressed with algebra.
Winding it back. Going backwards to prove that it's the case.
Yeah. There we go. So what am I going to do? I'm going to start with this number. Let's start it up here. We can use blue, black and blue. 1, 2, 3 is, I found out from the division algorithm, 17 groups of 7 plus 4. Notice that that's already a 7 to the 1 and a 7 to the 0. Oh. I don't know when I get excited like that it becomes a French but it does. It gets a French or Now what am I going to do?
Substitute. Yeah.
Oh, there he is. He's already on it. When you can see it, you can't hold it back. Everything in math is impossible or trivial. It's impossible till I see it, and then it's like, let me take over. Slow your roll. 17
Yeah, you got your own series to do.
is 2 times 7 plus 3 times 7 plus 4 times 7 to the 0. And so what we're going to do is we're going to distribute that in. What does that give me now? Distribute this 7. So now I'm using rules of algebra, and then we're going to distribute the 7 through the right. So then that says now I have a 2 times 7 squared plus 3 times 7 plus 4 times 7 to the 0. Right? And then what did I want? No, that should be it. That's exactly what I wanted. But what is that by definition? That by definition. Also, I always tell people when you're doing this, you don't need the penultimate, or you only need up to the penultimate row in this. You don't need the last row of this calculation. Same for the Euclidean algorithm. So I say box that off and cross that crap off. It's harder to censor yourself than you think. So you don't need the last row, but then you cleverly put the quotients in there, and then what do we get? That by definition is 2, 3, 4 base 7, because in base 7 you do 2 times the 7 squared times the 7 to the 1 times the 7 to the 0. So that by rote is the proof of the actual theorem. First I would use division algorithm and use the quotients till I get a 0 quotient, and then you'll know that you'll stop. And then if you back substitute, not using the last row, but you back substitute all those quotients in there, you will get exactly by definition that 1, 2, 3 base 10 is 2, 3, 4 base 7. I don't even know. We haven't done an hour yet. It's like, no, that's it. We're out. I want to play.
Hey, your lectures, you let me know.
I think that's roughly where we're going to stop there. Next time, what we're going to do is, because my daughter has to do an etude and a bunch of stuff today, and I got to go hustle, and we got to take down a shed, etc. So it never ends. Well, we got to keep the stream same cat time, same cat place at least. We'll keep the running time, the start time the same. The end time will be different every time because I don't know what I'm going to say till I get up here.
Right.
But what we're going to do next time is we're going to start looking at, let's do a little bit more. Well, happy medium. I always try to talk myself out of doing less math, and I'm like, no, what are you doing, brain? Let's do a little bit more math, and then we'll go. So I talk myself out of it every time. at the beginning of classes at McEwen, I'm like, we're going to end today because I've had enough of this. And then by the time I start going, I'm like, no, give me a couple more minutes. Give me a couple more minutes. All right. Oh, I didn't do enough. Is it 1, 2, 3, 4, 5, 6? 1, 2, 3, 4, 5, 6. Okay, good. So when we do this, say we're going to add 0 plus anything is something. So I don't need to add zeros into the table. So when we do the addition table, we're going to have 1, 2, 3, 4, 5, 6. The 1, 2, 3, 4, 5, 6. And then this is the addition table, base 7, because you don't need the 0 in there. So then what we're going to do is we quickly notice that because this is a commutative algebra, that the table is going to be completely symmetric across a diagonal. This is how, if you're doing finite group theory and ring theory, this is how in the multiplication table you can tell whether something's abelian or not, whether the table is symmetric across a diagonal. If you don't know what I'm talking about, that was too much too soon. It's never too much too soon. Start wondering what I was talking about and what the heck, and go investigate for yourself. I said a bunch of key words there. Slow it down. Go look them up on Dr. Google. I'm sick of catering. Academia wants to cater to the half-wit and dumb it, water the vodka down until everybody can handle drinking it. No, this is what vodka tastes like. If you don't like it, stop drinking it. Get out of the room. 1 plus 1 is 2. That's good. 1 plus let's go. 1 plus 2 is 3. 1 plus 3 is 4, 5, 6. Now, when I want to do 1 plus 6, that's going to be, what's 1 plus 6 in base 7? That's going to be 1, 0. Now, also, it's symmetric, so what that means is you can do that quickly down here. You don't have to think down here, down the column. Now I'm going to do 2 plus 2. Oh, Barney, Barney was right about some things. 2 plus 2 is 4. You're right, Barney. But you love me, I love you, then we're happy family. You liar. That was, love is not symmetric. That one's not true. I'm not bitter. This is 5, 6, and now what are we going to get? 2 plus 5 is 7, which is 1, 0, and then 2 plus 6 is 8, but 8 is one group of 7 plus 1, 1, so that's 1, 1. Also, it'll be the same all the way down, 5, 6, 10, 11. So it's not 10 anymore. That's you need a new name for, like, that's one group of 8 plus 0. But now you can see the pattern. You get 6, 10, 11, 12, 10, 11, 12, and then we can get 11, 12, 13, 12, 13, and then we get 13, 14, 14, 14, 15. And remember what that means is 6 plus 6 is 12 in your regular familiar land, but 12 is one group of 7 plus 5 ones, which would be, because I can calculate that one in my head a little bit faster, which is exactly 15 base 7. So this is what I claim that you really need to, especially if you're going to be a K-12 teacher. There's no a priori knowledge that 6 plus 6 in base 7 is one group of 7 plus 5. 6 plus 6 is 15 now. You don't have 15 apples, though. You have 12 apples. You need to figure out how many apples you have in the basket. So you have to make kids, I will rarely say it, but you have to make los niños memorize the addition table and the multiplication table, because all further computation from here on in relies on the addition table and the multiplication table. I say in my exams, when I give this in the history of math or in the Math 160 for education teachers, I say, as long as you promise to make kids, force them to put this in their brain in base 10 and the decimals and the multiplication table, I will give you these tables on the exam so you don't have to think, because this is what you're relying on. Because now if I want to do 1, 2, 3 plus, can I bait you? What's wrong with that number? You're not allowed to have 7s. You can't have 7s. So if we're going to add this in base 6 or base 7 now, what am I doing? I'm saying I'm going here and I'm saying 6 plus 3 is this number, 1, 2. So what is that? Because 6 plus 3 now became a 2-digit number, I can't cram a 2-digit number here. So all it added to the 1 spot was a 2, and we have to carry the 1 over to a group of 7. That's where we're carrying it over. Now, kitty, kitty, There's another kitty. I hear you creeping up on me. 5 plus 2 is 1, 0. So if you want to do it in your head because you trained that way, 5 plus 2 plus 1 is 8. But 8 in base, there it is. It's the 6 plus the 2. 8 is an 11. So I'm going to get a 1 and carry a 1 again. And then luckily, 1 plus 1 is 2. So I get 2, 1, 2. Oh, we got 2, 1, 2. That was a new code in area code in 2, 2, 1, 2, something like that. I wanted to leave one of those up. We could do 2, 1, 2. There you go. It's like I just did up your kilt, go up your kilt. Have a good day. So that's where we'll. And next time, what we'll do is the multiplication table, and you'll see when we switch to multiplication times. What was the other number? 57. No, it can't be 7. When we do this, you'll start realizing that we're going to add zeros in the other ones, and then eventually we have to do adding also because multiplication is higher order addition. We're just doing it in a different base. So this is conversions between bases, and then next time what we'll do is we'll start doing arithmetic in the other bases, adding, subtracting, multiplying, and dividing. It's all addition. It's all Greek to me, and I can't speak very good. That's all I got. Except for a cat. Come here, kitty.
All right, thank you, everyone. Just pending Adrian snagging a cat. Did he catch it? Did he catch it? Nope.
No.
All right. Goodbye, everybody. Thanks for joining us. See you next time, next week. Goodbye.